I will speak about thermal field theory, and so first thing you may wonder is what is this all about? I mean, it's basically about heating up elementary particles. I mean, you have we consider elementary particles in the standard model, or maybe beyond, at very high temperature. And how do we get this? I mean, we have to heat something, for example. We can heat a cup of tea, for instance. And when you heat a cup of tea, the molecules start to move faster and faster. And if you heat it more, they will, it will evaporate, whatnot. And if you do the other thing, if you cool it, you will still see that there is something around. It will freeze at some point, but there will be always something. And this is because in a cup of tea you have some non-zero conserved charge, which is, for example, baryon. You can have this also in what I discussed today, but for simplicity I will assume that we have no conserved charges at all. So if we cool our system to 0 temperature, there will be nothing. But if we heat it up, then we get something. So we heat up in a certain way, we heat up nothing. But how can you imagine this? Suppose you have some container, and inside there is something, the elementary particles at very low temperature, so low that you have, I don't know, say room temperature or so, then the only things you can have there is, say, for example, photons and maybe neutrinos. So you have here a container with lots of photons. Now if you compress them, then you will increase the energy and you will increase the temperature. You should do this adiabatically so that it remains in thermal equilibrium. And if you compress more and more and more and more and more, the photons will have, say, energy of 1 MeV or so, but then if two photons collide, they can make an electron-positron pair. And then we don't just have a gas of photons, but also of some electrons and positrons. And if you heat up further, there will be many of them. If you heat up still further, you will at some point be able to create muons and pions, and even higher, you will you will dissolve the pions. They will get closer and closer, and they will break up into their constituent quarks and gluons. And then at even higher temperature, you may even make W bosons, Z bosons, and also maybe some new physics. And this type of systems you can describe using thermal field theory. Now, what is this good for? So what's the use of thermal field theory? Well, one important application is the early universe, where we have, we know that it was in very good thermal equilibrium at some point because we observed the cosmic microwave background radiation, and this has the most perfect black-body spectrum that we have ever observed in nature. So it means that it must come from a system which was very close to equilibrium. Now, where does it come from? Well, it was created when the universe cooled down, and such that the protons and the electrons combined to form hydrogen. And at that point, there were no more free charges in the universe, and the photons could travel freely. And that happened when the temperature was so the cosmic microwave background is from temperature which is it's roughly like the binding energy, a bit less than the binding energy of hydrogen. And if you look closely, then you find that is of order 0.3 electron volt. So you see, I use units where the Boltzmann constant is 1. So their temperature is measured in in electron volt. So throughout my lecture, I have Boltzmann constant equal to 1 and also the Planck's constant and the speed of light. Okay, so from the observation of the CMB, we know that the universe was in perfect, almost perfect equilibrium at this temperature. And there is one much older relic that we observe, which is the abundance of light elements, like far away from stars, which, I mean, most elements were made in stars, but if you are in a region where you have never seen a star, then there are only the nuclei coming from the Big Bang, and we can compute their abundance, the relative abundance of the, hydrogen, deuterium, helium, and lithium. We can compute it by assuming thermal equilibrium, and it works very well. So BBN, and this took place when the temperature was of order of the nuclear binding energy, of the binding energy. So this is from temperatures of order 1 MeV. So it's a huge ratio here, and we know that the universe was in thermal equilibrium at that time also. More we don't really know by observations, so but okay, we know the standard model very well, and so it's plausible that at even higher temperatures we had this situation. Now, another application is the relativistic heavy ion collisions. I mean, this is all nice, but this is not something we can make in a lab. But in a lab, we can collide very highly energetic nuclei, big nuclei, compress them, and so that you have a very large energy density, and that might or should thermalize. So this was cosmology application, and now heavy ion collisions. There we want to create a maybe thermal system made of quarks and gluons, and the temperatures we can achieve there are like at RIG, for example, it's been estimated like about 350 MeV, and at LHC, the estimate is that the temperature is, I don't know, like somewhat below or so, or like 450 MeV. So this is where we use thermal field theory. And now, obviously, it's crucial that, that if we want to talk about temperature, we need thermal equilibrium. So we also should understand why there is thermal equilibrium and when maybe the thermal equilibrium will no longer hold. And I already said here, if you do this experiment here, you should do it adiabatically. You should just do it very fast, because then the photon momenta will be distorted and it will be a non-equilibrium distribution. And also in cosmology, we don't have a system in a static box, but we also have, we don't have compression, we have expansion. And the expansion changes the momenta of the particles, so they could distort the equilibrium distribution. So we must understand whether there could still be equilibrium, and the criteria for that is that the particles interact faster than the expansion, so that they can stay in equilibrium. I mean, if the expansion was 0, then they would be, after some time, they would always thermalize. So if the expansion must be sufficiently slow to keep the system in equilibrium. So what can we say about that? about thermalization, which, by the way, is an interesting and very complicated topic, and it's a topic of current research, but I just do very primitive estimates here, and which just gives us a rough idea what happens. So if we start with cosmology, we have the Hubble expansion, which is given by the Hubble rate, which is the time derivative of the scale factor of the universe. Time derivative divided by A. So A is the scale factor of the universe, which tells us how, tells us basically how the distances change. This A dot here. This is H, that's the Hubble rate. And from GR, we know that the Hubble rate is given by the energy density of our system, rho, over the Planck mass squared. So rho is energy density, and Planck, which is roughly 10 to the 19 GeV, huge scale, as the Planck mass. Okay, so this from this equation we get, once we know the energy density, we know how fast the universe expands. Now, what is the energy density? So let's assume that the system is in thermal equilibrium, and to see whether this is consistent. So if it's in thermal equilibrium, then the energy density is determined completely by the temperature. So we have an equation of state, which tells us what rho is for a given temperature. Now, if we say the system is very hot, so that we can neglect the masses of all the particles, and if the interactions are weak enough, then we have an ideal gas, and the only scale of this ideal gas is the temperature. So then we know, I mean, this energy density has mass dimension 4, so it must be some number times the temperature to the fourth. Yeah, so that the Hubble rate, I'm sorry, this is wrong. This is h squared. Right, this has mass dimension 4, this has mass dimension 2, so this has mass dimension 2, because it's 1 over time squared. Yeah? Okay, so if we take the square root here, we get the Hubble rate, which is of order t squared over the Planck mass. Now, now we have to compare this with the rate that it takes to equilibrate the system, and so what we can look at is some interaction rate, call it gamma, which is determined by, say, scattering processes like this one here, for example. So you have some particle and, well, annihilation, and then creating another particle-antiparticle pair, for instance. And here we see that you have 2 vertices and you squared, so we have 4, which is like something like alpha fine structure constant to squared. So this could now be, if it could be QCD scattering, then this would be the QCD fine structure, and could be electroweak. And by dimension, so this is the interaction rate, is a rate, so it has mass dimension 1, and if we neglect masses, then the only scale that we have is the temperature. So that's our interaction rate, and so the ratio of interaction rate over the Hubble rate is, well, now we need some value for the coupling. So it's just very rough estimates. Say, assume that alpha is of order 10 to minus 2, for instance. It's a small number. Doesn't matter so much how small. Then alpha squared is 10 to the minus 4. And then we have, downstairs we have the t squared. So we have a 1 over t here. And then upstairs we have the Planck work mass, which is 10 to the 19 GeV, which gives 10 to the 15 GeV over T. Yes? Okay, and, sorry. Question.
Should it be mass Planck or 1 by 2? Because you, from going from h square to h, it should be mass Planck. Oh, there is a mass Planck square. I see. Okay, thanks.
Here? Yeah? Okay. Okay, so now this is, if you want to have thermal equilibrium, this should be bigger than 1. And here you see, upstairs you have a huge number. And if the temperature is, say, at electric scale or so, this is really huge. And this explains why the CMB is such a nice black body, because the thermal equilibrium is just extremely good. Only if we get to this extremely high temperature, which is like near the gut scale or so, then we may not be in a thermal equilibrium. Okay, so this is cosmology. What about heavy ions? Heavy ion collisions. Here we have, so we collide these two heavy ions, but once you create them, of course, they will very rapidly, the system will very rapidly expand, and then this quarks and gluons, they will hadronize and they fly away and end up in the detector. And so what I did to estimate the expansion rate is I said, okay, it's something like a hadronic scale where, say, or some scale which people find in simulations. So it's roughly of the order of like 1 inverse Fermi, which is like 250 MeV. Yeah, very rough. And the interaction rate the interaction rate should be something like, well, related to the temperature. No, sorry, this is the expansion rate. I'm sorry, this is the expansion rate. And the interaction rate, well, here we had alpha, the coupling squared times the temperature, but if we are at like few hundred MeV, then the strong coupling is really strong. So this is of order unity here, so that the interaction rate is of order T. Okay, so then the ratio gamma over T is, well, you see if this is the temperature which we reach at the LHC, then it may be, yeah, of order 1/2, say. Which means that it's not terribly big. So it's, no, sorry, it's not 1/2. No, it's to order 2, sorry. It's of order 2. So it's bigger than 1. So we can hope that it thermalizes, but it's maybe just so thermalizing. Yeah. That means that is from the point of thermal field theory, this is a very difficult problem, the relativistic heavy ion physics. Where? Here?
Left-hand side of this expression.
Hmm?
The left-hand side of this expression
Last line.
is not TH.
Gamma over H, sorry, H, yeah. Gamma over H, yeah. Thanks. Okay, so in my lecture, what I will do, I will always assume that we can use perturbation theory, which so that it usually applies relatively well to cosmology, but also we hope that we get some insight into qualitatively at least what happens in heavy ion collisions. So I will assume that here is some small coupling and that we can expand in this coupling. Okay, so what can we compute with thermal field theory? So first of all, the thermodynamics, of course, like the pressure, like rho energy density rho or pressure P, and also one thing which is interesting for cosmology, also heavy ion collisions, is to see whether there could be phase transitions. And phase transitions are something very interesting because if you have a first order phase transition, like from say from liquid water to steam to vapor, then no, was it just water to ice, for example? Then you have even if you can get into non-equilibrium because the system there may be so if you cool say water, then you can imagine then you cool it to freezing and then all of a sudden you get some ice and then it will spread over the system. So that means that you have a system which is not in thermal equilibrium and it's not even any more homogeneous and so on. And this is could be very interesting in cosmology because if you have only if you have a deviation from thermal equilibrium, you have really a relic from that epoch that we can see today. I mean, if everything was always in thermal equilibrium, everything would just be determined by this one number of temperature. We would see nothing else. So we always need, if we want to see something, some observable relics, we need some deviations from equilibrium. So that is an interesting application here of thermal field theory. And this afternoon we will hear something about baryogenesis, and baryogenesis needs non-equilibrium, and one way to get non-equilibrium would be, say, first order phase transition. Yeah, that's one of the things, so the thermodynamics, and the other thing is we can actually go slightly away from equilibrium, so we can describe close to equilibrium systems. Like, for example, like thermalization rate. So that tells you how long it takes to get back to equilibrium, or, for example, the production rate of particles of certain very weakly interacting particles, which, like some FIMPs or so, which are never in thermal equilibrium, which you can create from a hot plasma, but then after they were created, they just propagate freely. These are the type of things that are being computed. Okay, so I will try to explain how this here works in practice. I will show you the technique. I give you an idea of the technique that people use for that, and we will recognize things from previous lectures. For example, we get certain effective field theories to describe the system, and we will. I will always use this so-called imaginary time formalism, which I introduce in a moment. And this looks very much, it's tailored for equilibrium, but I will also show you that you can use it to, by analytic continuation, to get information about non-equilibrium systems. Okay, let's start, get to work here. So the central object in thermodynamics is the so-called partition function, which we have seen before. It's the trace of e to the minus beta h. H is not the Hubble rate now, it's the Hamiltonian of our system, and beta is the inverse temperature. So the pressure can be obtained from the partition function like this. So Z is equal to e to the plus beta times the volume of our system times the pressure. So E is the volume. Okay, now how do we compute this? We take this operator here, this statistical operator, and we have to take the trace. Now for the trace we can take any basis in our Hilbert space, and one convenient choice here is to say we take the field eigenstates. So we take states in which the fields have a given value. Say, for example, if you have electromagnetic fields, then you say that I just give the values of the electric and magnetic field, yeah, at a given time. Okay, and so we can write the Z as, and now we have to not just take a single field configurations, but we have to so to say integrate over all of these field configurations. So we get an integral of the type phi a. So phi a is a field configuration in three-dimensional space. And then we have here the eigenstate of the phi a, e to the minus beta h, phi a. That's our partition function. Okay, so far so good. Now the key observation is that you can, if you look at this object, you have e to the some number times the Hamiltonian, and this is something which looks a bit like a time evolution operator, because time evolution operator is e to the minus I times operator is e to the minus I h times the time t. And then we see that if we compare these two expressions, that we indeed have a time evolution, but not in real time, but imaginary time, from 0 to minus I beta. So we have, so here t is minus I beta. Yeah, so we have basically the picture that our state phi I evolves in imaginary time, and then you take the scalar product with the same state here. Okay, so what do we now remember something from our quantum mechanics courses? If you have a amplitude to go from a state phi A to a state phi B in a time t, this amplitude can be written as a path integral over all paths in field space of e to the times e to the I times the classical action of our system. So S is the action. And here in this integral, here the boundary conditions are such that at initial time, the phi is equal to phi A. So phi at, say, 0 and any space-time point x is equal to phi A of x. And at the final time t, phi of t and x equals to phi b of x. That is the famous Feynman path integral formula. And now we see here we have an object of this type. So we can also write this expression here as such a path integral, only that it's not evolving from real time 0 to the real time t, but from real time 0 to minus I beta. Yeah, so we find that the partition function is a path integral of e to the is with the with the boundary conditions that phi of 0 and x equal to phi a of x and phi at minus I beta and x. Now the difference is that here we have the same. I mean, here it could be any other field configurations, but here it's the same because we take the trace. There's also phi a of x. Yeah, and the phi is really a imaginary time-dependent field in here, and this boundary condition tells you that it's a periodic one. So we have a
I mean, in here, an integral over phi a.
over phi.
Phi a.
Here?
Z.
This is phi, what phi?
Yeah, so that is the matrix element on the right hand side. The path integral that you have written, that's for the matrix element. But then you have an integral over phi a as well.
Yeah, well, okay, so it's right. I mean, it's included in there. I mean, it's now initially you integrated over the phi a's, but now you integrate over all phi a's. I mean No, I'm sorry. I should leave this out. This is your point. Yeah, sorry. No, okay. Yeah. It's the same. The point is that it's the same, right?
So you basically have to write phi 0x is equal to phi minus I beta x.
Yeah, sorry. Yeah, you're right. Yeah, thanks. Yeah. Yes, thanks. Sorry. Okay. Yeah, that's our path integral, and it looks like it's complex, but in fact it's not, because here in the path integral we have the action is now given by integral from 0 to minus I beta times d tau dt times integral d3x of Euler-Lagrangian, and now the dt is minus I times integral from 0 to beta d tau d3x of L. Yeah. So IS is real, and it is the reason why this is easy to compute also on the lattice. Yeah, because now we have not a complex phase in our path integral which oscillates wildly, but we have a real weight, so we can in principle treat this numerically. And this is what many people do. But it's also very useful for perturbation theory. Very convenient. And that's what I want to show you now. So how do you do perturbation theory in the path integral? Well, it works as usual. We say now we have our Lagrangian contains a free part, which would describe free part non-interacting particles, plus some interaction, and then we correspondingly would have S equal to, so if we write that, is equal to path integral d phi e to the is is now the action for the free fields plus the interaction part. And that's a nice thing in the path integral. Perturbation theory is so easy. You just take, I mean, this is just, these are C numbers here. You just expand in S interaction. Yeah, so you can write this as integral d phi e to the is naught. And then this is the lowest order. And then you get the first correction, which I have here I as interaction and plus higher orders. So here we see the first time term is the partition function at zeroth order. So we can write this as z0 times 1. And then here we can interpret this here now as 1 over z0 times the integral of that, which is like an expectation value of the interaction, and then plus higher orders. So what I define here by this expectation value is of anything, any operator A is defined as 1 over z0 times the path integral of d phi e to the I s naught times this operator A. Yeah, so this way one can, if you have a small parameter in your interaction Lagrangian, you can expand this in this small parameter this way. Now,
so that's vacuum expression value? That's vacuum expression value? Or you?
No, it's not.
Put
I mean,
non-trivial boundary conditions?
It's sorry. Yeah, of course. I mean, the boundary conditions don't change. They don't change. They are the same. So it's a thermal expectation value. Yeah. I mean, I only didn't change the integration measure or boundary conditions, just what comes up behind. Okay, now you might be tempted now to use this formula here to compute the pressure and using the path integral. And some people do that. And it turns out to be, what I mean is just the lowest order term here, which should be very easy because it's ideal gas. But if you want to do it, if you do it with the path integral, it's really a pain. It's very complicated, and I always tell people, then better don't do it. If you want to compute the pressure of an ideal gas, then you should not use the path integral, because the integration measure is, I mean, you have to be very careful that I don't want to talk. I just warn you not to do it. So if we apply this to the pressure, say then we should better just use what we have learned about an ideal gas, about Bose statistics and so on. And for massless particles, so for let's say one scalar field, or one bosonic degree of freedom, then the pressure, again, like the energy density, has mass dimension 4, and so the pressure must be simply some number times g to the fourth. And if you just use, well, you can look up Landau-Lifshitz, for example, there you find it, and if you can also try it yourself. The coefficient is pi squared over 90. So that would be one exercise suggested, that you remind yourself, how do you get this type of expression? I mean, there's an integral at the end of the day, and you can, I don't know, you don't have to do the integral, but just to try to get at the right integral expression for this. So check this here. Okay, now this was for massless particles. Now we can use this here. We could also get it from Landau-Lifshitz from non-zero mass, but it's actually instructive to use this perturbation theory here to compute, say, the first correction to this expression. If you have a non-zero mass, but which is much less than the temperature, then there will be a correction here, and that you can obtain using perturbation theory. So we use perturbation theory to determine M-dependence, M-squared corrections. And yeah, one thing, the way I'm going to do it is I say, okay, I include, so I have my Lagrangian and I have a mass term. So I have L mass is minus 1/2 times A mass times phi squared. Now what I do is I say I add a small correction to my mass squared, so we replace m squared by m squared plus delta m squared, and then treat this here as a small perturbation. Yeah. What happens then? Remember, the pressure was e to the the partition function was e to the beta v times the pressure, and now we get here the 0th order pressure plus some correction coming from the delta m squared here. Now this term is supposed to be small, so we can Taylor expand to first order, and we get e to the beta volume times p naught times 1 plus beta v times delta p. Okay, and that must be, of course, the same as this expression. We also have this, now S interaction is the action due to this delta m squared here. Yeah?
So when you do replace m square by m square plus delta m square, you at the leading order you first get the right hand side, and then m square plus delta m square can be resummed to completely, and then you will get the left hand side.
Yeah. Okay, so here we have this prefactor is just a 0th order partition function. So what we get is that beta times v times times delta p is equal to this expectation value of I S8. So what is the right hand side? We can the IS int is minus 1/2. Then we have the integral from 0 to beta d tau, integral d3x. And in S interaction we have the delta m squared times the phi squared. Okay, now phi squared of x, of minus I tau on x I should write. But we assume translational invariance in space and time, and then this thing is the same as, so it's independent of tau and x, and so this here, this integral just gives the volume, and this integral gives here the tau. So what we find is that the delta p is equal to minus 1/2 and times the delta m squared times the expectation value of phi squared evaluated at any time and space-time.
So
or you can translate this as, yes?
Just a nice question. Could you do this only with the kinetic term, the variation of the kinetic term? Is it possible to do that way without introducing m?
Well, I mean, the kinetic term sits here and determines what this is. I mean,
Yeah, you are introducing a parameter m to do the variation.
Yes, that defines my perturbation. Yes.
Right. But actually, delta m square is exactly, fully summable. So in spirit, we should be able to do the same thing with the kinetic term only.
I could do the same thing.
I mean,
I could do the same thing, but this doesn't tell me how I have the thing depends on the mass. I want the mass dependence. So I'm after the mass dependence of the pressure. So that's why I do this. So because
the first expression is for m equal to 0, left hand side, at the top left.
this is for mass. This, yeah.
Yeah. I'm just trying to see what introducing the mass, what is it doing, non-trivial thing.
That will we see. That is the interesting question, right? What we will, well, we will see what it does. I mean, we will understand that without calculation, but it's also a nice thing to see how the technique that we now use for perturbation theory. That's so. But first, let me.
So one question, sorry. Here. So maybe it's naive, but so the volume also itself can change, can it? I mean, if we think of the expanding universe, the volume.
No, actually, yeah, thanks. I'm now. You see, I mean, I'm really. This is strictly speaking for a finite box, for a fixed static box.
Okay.
Static, but the volume will drop out, so I mean the box can be as big as you like, and here we have, in a way, assumed that the expansion is so slow that it doesn't affect this. I mean, I said, in the beginning I said that one gave criteria when expansion is considered to be slow, and here we assume that it's so slow that we can forget about it.
Okay, but in case of, say, universe, do these mass corrections also have impacts on volumes? Or
Yeah, sure.
they do? Okay. Okay, thank you.
Yeah. I will come to the, well, maybe.
I have a question
Yes.
here. So the last second line where you write replace m squared by m squared plus delta m squared, it is basically 0 going to 0 plus delta m squared, right? Because you write p0, which is p0 is what?
No, okay. I mean, okay. This is in a way more general than this here. I mean, what I have here so far can also be in perturbation around a non-zero mass, which I'm free to do. I mean, it's slightly more general than I need it, really.
Yeah.
But you will see why I do this. I have more information enough from it.
Okay, what I was thinking is probably we are trying to get them. I mean, initially we had the pressure for mass is equal to 0. Now we are looking for delta m corrections. So on m is equal to 0, but you're now saying that it's for any non-zero m.
I'm at this point. At this point for me, the P naught is really the pressure at finite mass m. And
Yeah.
then I add a correction on top. So let me maybe it's more clear if I rewrite this expression in a certain way.
I think the confusion is arising from the notation that you are not writing m0 but writing p0. So if you write m0, I think we'll be okay. Like m0 going to m0 plus delta m square. So but doesn't matter. But that is why
because
the
this
question.
defines. Oh, I could do that. Yeah, but then I have to write more.
I'm not suggesting you to do this, but I'm saying that this is what the question.
Yeah. I mean, it would be more clear if I would write here. So m0 squared plus this, and then this m0 squared determines this. Yeah. Okay. Do you allow me to leave this?
Yeah, I was not suggesting you to do that. I was just saying that is the question. That is how the question arises.
Okay. So, but if you have this remember this, then what this expression tells you that the derivative dp with to dm squared over dm squared is given by minus 1/2 times the expectation value of phi squared. Yeah. So that's a formula which says that if I have a system with a high temperature with mass m, then this formula gives a relation for the mass dependence of the pressure. Yeah. Okay. Now, what is this phi squared? The phi squared is an expectation value of two fields, and we have in perturbation theories oftentimes see these things. So there's two-point functions. Say if the field is at two different points, this is the so-called propagator of the field, which is I call delta of x, say x, phi of x, phi 0. And so this phi squared, it means that both phi's here have the same argument, so this would be the propagator at 0. So dp dm squared is given by minus 1/2 times the delta, the propagator at x equal to 0. So x means for me that includes the time and the space. So imaginary time and the spatial coordinates.
Sir, one question. Sir, here. Yeah. So you did the d tau and dx integral in the above part by assuming translation invariance.
Yes.
But what does it mean to assume translation invariance in imaginary time?
Well, the same. I mean, it's just if you have, I could write this more explicit in the it's a great exercise, actually. So if you are more general, so it means that if you have phi of minus I tau 1 x1 phi it's the same as phi okay, that it's what it means. And what I will, what you see here is like, for example, if yeah, so in principle, if you always want to apply this equation, you may also encounter negative values of this here. And so far we have only introduced this for positive values. And one thing one should know is that that's another exercise now. I mean, we introduced the propagator here in the path integral picture, but we can also define it in operator language. So in operator language, we can we have so far only computed the partition function. So if we have an expectation value of any operator, or how should I write it? Yeah, or which can also be a composite operator. We define the thermal expectation value A as 1 over the partition function, and then times the trace of e to the minus beta h of this operator. I mean, that's the usual definition of thermal expectation values. This is now an operator, and I mean, to distinguish it from this type of expressions, I don't have an index not here. Okay. Now we can also do this for the propagator. So we can here put, instead of A, we could put a phi at one point and a phi at another point. And then what corresponds to this here, to these expressions, is actually the time-ordered, imaginary time-ordered propagator. So imaginary time ordered propagator. That would be phi of x, phi of, say, x prime, so x1 and x2. Maybe I should write it by phi of x2. And here I put the time ordering, but it's in imaginary time, or sometimes people also call this Euclidean. So I call it Euclidean time ordering. That is defined as theta of tau 1 minus tau 2 times the expectation value of phi x1, phi x2 plus the, if the tau 2 is the bigger time, then the phi of x2 comes first. So it's theta of tau 1, tau 2 minus tau 1 times phi x2, phi x1. Yeah? So that is the propagator and operator language. And what I would like you to check is, if you use this expression, so, and the first thing you should, you should explain that this equals our, what I defined as the delta of x1 minus x2. And what you should also see is that delta of minus I tau x is periodic in tau with period minus with period beta. Yeah. And if you have a lot of time, you could also check that if you had not a bosonic field here, but a fermionic field, that the propagator is antiperiodic. So this is maybe a bit too much, but if you are interested, antiperiodic, that's straightforward, but of fermions. And I mean this, to use this for all tau 1, tau 2 between 0 and beta, you should really think of this propagator as a function living on, so this is here for for this propagator here to live on the interval from minus beta to plus beta. Yeah, so
actually all calculations are periodic, right?
Hmm?
All calculations should be periodic, right? The path integral, it's because of the definition, the path integral.
Yeah, right. Okay, so you will see that this thing is automatically periodic, but we also see that it's periodic because we have this periodic boundary conditions of our path integral. So that means now back to the path integral. This was for operators. So now we go back to the path integral. Then, because of periodicity, we can expand the field in a Fourier series and it's conventional to have a factor t out here, and there we have e to the minus I omega n tau times, it's a bit dark here, times phi, maybe I should write it on the next board. So phi of minus I tau x is a T temperature times the sum over n over all integers I to the minus I omega n tau, and then fields phi n which only depend on space. I mean, it's like a Fourier transformation, well, it's like a Fourier series in time. And these frequencies here are, since the period is beta, the frequencies are n integer times 2 pi times t. Yeah, so beta times t is 1, so if I insert here beta, I get n times 2 pi. And these frequencies are called Matsubara frequencies. Okay, so then so in the Fourier transformation, say, of the propagator, you usually have an integral over frequency, an integral over spatial momentum. But at finite temperature, in this formalism, you have a discrete set of frequencies. So you have a sum instead of an integral, and then still an integral over spatial coordinates. Yeah, so the propagator can then be written as delta of x is, I mean, usually you have in Fourier space, you have here, would here have the integral over frequencies, but now you have this Matsubara sum, and then you have the integral over spatial momenta. So this here, this I will use oftentimes, so that is the integral over d3k over 2 pi cubed, momentum space integral. Yeah? So that's the difference compared to zero temperature, that here you don't have an integral, but this sum. And then the propagator looks just as usual. It is 1 over, so here we have the spatial momentum squared plus the mass squared, and then here comes the frequency, here's then minus the frequency, but now the frequency is imaginary because this here, I mean, if you write this in terms of imaginary time, you can think of this as imaginary frequency, so you have here plus omega n squared. Yeah, so it's like in a Euclidean space-time. Okay, and then we are kind of ready to evaluate this expression, because we now have this integral expression for the propagator. Sorry, I forgot something important. It's a Fourier transform. I forgot the exponential. Here you have e to the minus I kx, so it's, in this case, it's minus I omega n tau, and then minus I, no, plus I k dot x. Yeah, I mean, that's the usual Fourier transformation, and this is the usual momentum space propagator. Okay, now here we have the propagator evaluated at 0, and then in fact the numerator here is just 1. Yeah? So what we find is that dp dm squared is here minus 1/2, and then t times the sum over n and integral over k 1 over omega n squared plus k squared plus m squared. Okay, now we have to compute this sum here. And this is a problem that you oftentimes encounter if you use Matsubara formalism. And I still hope I started a bit late. Maybe I can still explain how I compute these sums. Okay, I try. That's an important tool. Now,
sorry, I missed one thing in this. So this delta x, it's only x vector.
Where are you?
Yeah, the last propagator. Last line. Yeah, there. That's x. What? Sorry, I missed the notation. So there is no t or beta in tau or beta involved here. What was the? Yeah, this tau, w and tau, omega and tau, right? Yeah. So here in dp dm square, what is the status?
Oh, that's this expression here. That is this. This is the derivative of the pressure with respect to mass.
Right. So tau dependence I'm looking for.
There's no tau dependence here.
Yes, so I'm saying what is x? You're setting both x and tau to 0. I'm not following this.
Yeah,
notation.
I mean it's using. Okay, so this is. This is what we have to compute, which is I said is here. This is the same as phi squared at. If I have translational invariance that I argued, this is the same as phi squared at 0, and this is why I can put it to 0. And okay, maybe it's more intuitive if I write a Feynman diagram for this, because so this is the propagator. Let me just. So the propagator is usually written like this, for a scalar with a line. So here's point x and point 0, and then this here would be like this type of diagram. So the propagator closed in itself, so that it's the same. Yeah.
So your x without an arrow means both space and time. Sorry, imaginary time, right? Right. Yeah. Just to confirm that. Okay. Yeah. Fine.
Okay. Yeah. So how do I do Matsubara sums? The trick is the following. You remember the Bose-Einstein distribution. It's this one. It has poles. For example, you see a pole at, if you take omega to 0, then the exponential becomes 1 plus beta omega, then the 1 goes away, and you get a t over omega for small. So for omega to 0, for omega or omega less than t, we have f Bose is equal to t over omega, so it has a pole at 0, and on top of that, it is periodic. In imaginary frequencies, so f Bose of omega plus I omega n. If I take one of these Matsubara frequencies here, then I e to the I beta omega n is 1. So this is the same as f of omega. So periodic in imaginary direction. So that means that the Bose function has not only the pole at 0, but it has poles at all Matsubara frequencies. So omega 1, omega 2, and then here minus omega or omega minus 1, for example. So they are all poles with the residue t. Yeah, and now the trick is, now you integrate. So if you if you want to do the sum here, it just, you can think of this as doing a contour integral with around all these poles here. So with a, so if you have a Matsubara sum t times omega n of some function I omega n, that is, you can write as a contour integral around this contour here, C prime, call it C prime d omega over 2 pi I, and then the Bose distribution function of omega times this function h of omega. Yeah. Yeah. So if I apply the residue theorem for all of them by shrinking the circle to 0, I get just h evaluated at the poles, and that gives me this sum here. Now it's convenient to put here a constant, which does so something without a pole. That doesn't change the result, because if you shrink the circle around the constant, you get 0. So here you have the plus 1/2. I include it. It's a bit arbitrary, but we will see in a moment why it is useful. And yeah, then so we have then this integration contour, and then we deform this contour like this. We can make the circles bigger, so that so here are our poles. This is again, so this is the complex omega plane here. Same here. So when we make the circles bigger, they percolate at some point, and then the contour becomes this one. So the sum, now this is the contour C, I call it. And so the sum over n, h of I omega n, h of I omega n, is the integral along the contour C d omega n over 2 pi I times 1/2 plus f Bose omega times h of omega. And now the trick is to, we can now deform the contour if there are no other poles, we would say just get 0. But if so I can move these two branches of the contour this way. But if we hit poles, we get contributions from these poles. And you see, this expression here has indeed poles and real frequencies. So remember, now I have in this expression there, I have now in here I have to replace the I omega n by omega. That means I replace omega n squared by minus omega squared. So 1 over minus omega squared plus k squared plus m squared has poles at omega equals plus or minus the one particle energy Ek, with Ek is square root of k squared plus m squared. Okay, and what you then can do is you can, so here are more poles. What you then can do is replace this contour here by the contour around these poles and evaluate them there. Yeah, and then you have performed the integral. And so maybe I should stop here and continue with this tomorrow.
I think you forgot a t in that expression on the left hand side.
Here on the here. Yeah, sorry.
Yes.
Yeah, thanks.
the and the zero temperature, the difference is like there is a summation, and that comes from the fact like you compactifying the time dimension.
Yes, yeah, it's a compact, right, yeah. It's like on a torus, yeah. Yeah, can you then, I mean, that's, yeah, you can, that's the best way to view this. I mean, you start with your imaginary time contour, but then you identify the endpoints, so it's like a, yeah, you can think of this as a circle in time.
So this use of Bose distribution is just to pick the residues at the Matsubara frequencies, and right? Is that right?
The what residue?
The use of Bose distribution,
Yeah,
FB.
that's yeah.
Yeah, but that's not unique, is it, right?
Why?
I mean, I could invent some other functions.
That's a very interesting question. I mean, it's a bit of a mathematical function. I mean, of course, you need that it doesn't grow if you go to infinity, and but
ultimately,
so how's it? I mean,
ultimately, you are getting two lines.
I mean, the poles and the residues are all fixed, right? Because the
right.
that you need to have, and of course, we already saw that it's not unique. I made a very good any constant, and the question is whether I could put something more than a constant. I don't.
You could
probably
do that. Yeah.
I probably not. I don't know, but I don't have a good answer now.
I think you could do that, but there must be some, I don't know, some reason for choosing. Is it true that ultimately you are getting two parallel lines only?
From here.
Yeah.
Well, you merge them.
The sum of all these circles basically is two parallel lines in opposite directions.
Well, you can move. I mean, the assumption here is, of course, that there are no other singularities in the neighborhood of the imaginary axis. That you can do this, yeah. Otherwise, it will be problem. That's the question. No?
That half that you've put, half plus the Bose-Einstein factor, that half you have not made any use of, right? You have not made any comment about how will it be useful.
If in the next step you will see how useful the 1/2 is.
Okay. Okay.
It's I mean, the point is, okay, so I can tell you why it's useful to put the 1/2. This function is an odd function of omega. And as the effect of this pole gives precisely the same as this pole. If you hadn't done that, then you would have to, it would be, of course, the sum would be still the same, but this way it's easier calculationally.
Okay.
There are sometimes problems where it's better to have other constants when you have to make, I mean, to be able to move this to infinity, the integrand has to fall off, of course. And sometimes you need other constants there to ensure this.